Hi and welcome back to my YouTube channel. In this video, we will talk about electric transformer. A transformer is an electric apparatus designed to convert alternating current from one voltage level to another. It can be designed to step up or step down voltages and works on the magnetic induction principle. The intention of this video is to try to explain the working principle and basic construction of a three-phase electric transformer, starting with the very heart of each transformer, the transformer core. As we say, the transformer core is the heart of any transformer. The material used for the construction of three-phase transformer core is silicon steel, which has high permeability. The core of the three-phase transformer is usually made up of three limbs in the same plane and two yokes, which are vertical parts of the core. Transformer core is designed to provide a path for the magnetic flux to flow around, which is necessary for the induction of the voltage between two windings. The core of the transformer is made of thin insulated steel laminations. These steel laminations are stacked together and then, these stacked laminations form limbs and yokes of the transformer core. Reducing the amount of energy losses due to eddy current is the reason why transformer core is made of thin steel laminations. So, what is the role of the transformer core? The role of the transformer core can be seen through the basic working principle of the transformer. The basic working principle of the transformer is electromagnetic induction. According to electromagnetic induction, some variable magnetic flux acting on coil loop will induce in this coil electromotive force. Also, fluctuating magnetic field can be easily produced by coil and alternating EMF system through this coil. To better understand how magnetic field in coil will look, we must take a closer look at current-carrying conductors. Current-carrying conductors produce magnetic field around it, like shown in the figure. If we implement this to our coil, then magnetic field of the coil will be as shown. To explain, when alternating current passes through this coil, it generates magnetic field. This magnetic field will fluctuate like alternating current fluctuates. This magnetic flux can be easily linked to secondary winding with help of transformer core. Fluctuating magnetic field of primary winding will induce an electromotive force in secondary winding due to the electromagnetic induction. Windings are made up of turns which are connected in series. Due to such construction, total induced EMF of winding are sum of the individual EMFs induced in each turn. Because the same magnetic flux passes through the primary and secondary winding, the EMF per turn for both primary and secondary winding will be the same. Of course, this relations apply for ideal transformer. Value of induced EMF per turn is given by equation like shown. If the number of turns in primary and secondary windings are N1 and N2 respectively, then induced EMF in primary and secondary windings are given by these equations. From the equation for induced EMF of primary and secondary windings, we get next relation like shown. This relation is called the EMF equation of transformer. We can replace right side of this equation with constant K. Constant K represents voltage transformation ratio K, as you can see. Transformation ratio K determines whether the transformer step up or step down voltage level. If number of turns of secondary windings N2 are greater than the number of turns of primary windings N1, then transformation ratio K is larger than 1. As you can see in relation, therefore we have a step-up transformer. If the number of turns of the secondary windings N2 are smaller than the number of turns of the primary windings N1, then transformation ratio K is smaller than 1, as you can see in relation. Therefore, we have a step-down transformer. The power, energy flowing per unit time, associated with both coils is given by this relation, and this quantity is the same in either coil. So if the voltage goes up, current comes down. Energy is conserved. 3 single-phase transformers we can replace with one 3-phase transformer, but with slightly different configuration. First winding near core is primary winding, and this winding sits concentrically around the limb. In case the step-down transformer primary winding is high voltage winding. In most cases, insulation between primary high voltage winding and magnetic core is some kind of oil-impregnated solid pressboard. The main function of this insulation is to prevent physical contact between the core and windings and to prevent mechanical stress developed in winding, which has crushing force on core material. As we have already learned from single-phase transformers, alternating current through the primary winding of each phase produces a continually changing alternating magnetic field that surrounds the winding. This magnetic field is linked with a secondary winding by magnetic flux which flows through transformer core. This magnetic flux will induce in secondary windings electromotive force (EMF) due to electromagnetic induction. Secondary winding sits concentrically around primary winding. Also, we must mention that there is insulation, oil-impregnated solid pressboard, between primary windings and secondary windings. Insulation is needed to prevent physical contact between the windings and short-circuit fault. It's good to know that disc-type windings are primarily used for high-capacity transformers, like this one. Disc-type windings are made of concentric discs connected in series using inner and outer crossovers. Primary windings, in this case high-voltage windings, are connected in a delta configuration. The delta configuration has the 3 phases connected like in a triangle, and delta configuration is formed by connecting one end of winding to the starting end of other, and connections are continued to form a closed loop. 3 phases are taken out from the coil joints. Voltage and current of delta configuration are given by this relations. Secondary windings, in this case low voltage windings, are connected in a star configuration. In a star configuration, all 3 phase conductors are electrically connected at one end. This end forms the center point. Center point is referred as star point. Neutral conductor N is drawn out from star point. The free ends are connected to the external conductors L1, L2, and L3. Voltage and current of star configuration are given by this relations. Delta star connected transformers are widely used in power distribution. To receive or bring out electric energy from transformer, we need insulated bushings. Transformer bushings provide a very effective insulation between line conductor and earth tank. The transformer core is mounted on a metal frame, with flanges extending along the bottom of the frame. The purpose of the frame is to support the coil and to relieve stresses and reduce the no-load electrical losses. A metal frame is attached to the body of the transformer. While transferring power from primary to secondary windings in the transformer, various energy losses happen, like eddy current loss, hysteresis loss, and losses in copper. All these energy losses are dissipated as heat. To prevent this dissipated heat in an electrical transformer, we use transformer oil. Oil-immersed type of transformer are filled with oil through a conservator and Buchholz relay. Transformers' oils are usually a high refined mineral oil. Primary functions are to insulate and cool the transformer. Oil must therefore have high dielectric strength, thermal conductivity, and chemical stability, and must keep these properties on high temperatures for extended periods. The oil in the transformer dissipates heat via natural convection through transformer coiling tubes, where oil circulates and cools down. When ambient temperature rises, the volume of oil inside the transformer increases. A conservator tank of transformer provides adequate space to this expanded transformer oil. It also acts as a reservoir for transformer insulating oil. The Buchholz protection is a mechanical fault detector for electrical faults in oil-immersed transformers. The Buchholz gas relay is placed in the piping between the transformer main tank and the oil conservator. Buchholz relay reacts when any fault occurs inside the transformer. The transformer oil gets decomposed and gas bubbles are produced. These gas bubbles move towards the conservator through the pipeline and Buchholz relay reacts on this fault. The purpose of pressure relief valve is to relieve the internal tank pressure. When a transformer develops an internal fault or some other condition like high heat or partial discharging, the internal pressure can cause a tank rupture. A pressure relief device will open when the internal pressure exceeds the valve spring force. This allows the tank pressure to vent to the atmosphere. There are also various measuring devices on the transformer that measures temperature and pressure inside the transformer. I hope that this video about electric transformer was very educational for you.